All right, we're going to talk a little bit about capacitors. You can see I started with a few pictures of capacitors. On the top left-hand side, you can see some examples of capacitors. They have those two little leads off the side like that. One is shorter than the other. We use them for all kinds of things, usually when we have to store electric charge that we want to retrieve later. On the top right-hand side, you can see that there's a capacitor used for a car stereo. If you need a lot of extra power in your car stereo, you want to make your subwoofer boom, then usually your battery can't provide enough, and even your car running can't provide enough power or enough electric current to make it run, so they hook up a capacitor. You can see the capacitors hooked up there, the big blue thing. You can also see that there's another time that you might want a big burst of electricity. That's in a flash. You can see on the bottom right, there's a picture of a camera cut open with a little cylinder sticking out of it. That's a capacitor also. And that capacitor stores up charge from the battery when you push the little flash button or whatever, and then kicks it right out. There's something similar inside your phone, but it's not a circle like that. The phone just doesn't have the room for a circle like that. What it's made up of are parallel plates of opposite charge. You can see that the two plates in the picture on the right have space between them. In this case, the space is filled with a vacuum. It's connected to a set voltage. You can see there's a battery on the left, and there's two wires connecting it, one to each one. Well, it's connected to again, it's showing a positive current. Even though we know positive charges don't move, remember conventional current deals in positive charges. So positive charges are going to go through the wire to the positive plate on top, and that's going to repel negative charges the other way. Or I'm sorry, it's going to repel positive charges from the bottom plate back over to the battery. That process continues until the voltage of one plate the voltage of the two plates is equal to the voltage of the battery. You can see what happens if you compare the plate on the left with 4 charges on each one to the plate on the right. There's a lot more than 4 charges on each one, but they are equal. It's going to collect an equal and opposite charge on each plate. And eventually there's going to be a point that those charges all repel against each other, and that's going to stop it from moving. So when they're equal, and when you take those charges and you hook them up to a circuit with nothing else in it, you can actually get the electric charges and the energy stored in the potential energy between those charges to come back out and power something like a car stereo or a flash on a flash bulb. As we know, we've looked at these a bunch of times. Parallel plates have an electric field between them that is constant, again, except for the edges, and they're going to collect a total charge of Q on the left one, the picture on the top right, or negative Q on the other. Remember, they'll be equal. And the electric field between the plates is constant, again, as long as we stay between the plates. And we saw earlier that the electric field is going to depend on the voltage and the distance between the plates. Okay? If we have more voltage, we're going to get a stronger electric field. If we have more distance between the plates with the same voltage, we're going to have actually a weaker electric field. But more voltage is going to make for it. And as we saw in the other picture, if you put more voltage on it, it's going to make a greater surface density. There's going to be more charges per square meter or square centimeter on the plate, just because there's going to be more energy per charge. So they'll be able to counter the potential energy that would naturally occur between equal charges that are collecting on a plate. And you can see it just uses the equation that we derived with Gauss's law, E equals sigma over 2 epsilon naught, to calculate what the electric field is. Remember, we did that with the little shape that we put in between the plates on one of them but not both of them. So it's the same thing we saw before. Now, in order to rate these, we use a concept called capacitance. Capacitance actually tells you how many coulombs of charge you can fit you can actually stuff onto one plate per volt of potential difference. Because if you use more volts, you're going to get more coulombs. And it's good to describe the ratio by which that happens. Of course, there are upper limits, and we'll talk more about those in later units. But the basic idea is that the capacitance is going to be the total charge that you fit on the plate per volt that you attach. So it's C equals Q over V. You can see we listed those things on the bottom. The units for capacitance are farads. Farads are just coulombs per volt. Now, if they ask you to calculate charge and they give you the capacitance and the voltage, you can do that using Q equals CV, as you can see on the bottom. Now we're going to look at the simplest case of this, a parallel plate, the parallel plates that are actually flat. You can see in the picture on the right that there are two parallel plates, conductive. They list something in the middle called a dielectric. The dielectric for us right now is a vacuum. In real life, they actually jam something in there for space constraints to make sure the distance stays the same, and for another good reason that we will talk about later. You can see that each plate has an area of A. That actually matters because the more area A that you have in each plate, the more charges you can cram on there. If you have a certain surface charge density, more area means you'll get obviously more charge on each plate. The distance between them turns out to matter too, because remember we said that when you hook up the battery to the conducting plates, to the capacitor, that it's going to push positive charges onto one plate and drive positive charges from the other. Well, that force depends on distance, like we saw in Coulomb's law. So if you put the plates closer together, not too close together, obviously, because if they're right on top of each other, then it's not a capacitor. It can't store any charge. It's just a block of conductor. But if we put them closer together, we can actually get it so that the charges repel more effectively. So we can actually hold more charge on them. When the plates are closer together, we get more capacitance. And there's actually a relationship between all these physical quantities and the capacitance. And you can see it down there. It's C equals epsilon naught A over D. Epsilon naught is an old friend of ours. We used it in Gauss's law. It's the permittivity of free space. Remember, it's like 8.85 times 10 to the negative 12th. Area is the area of the plate in meters squared. D is the distance between plates, also measured in meters. So you can use those to calculate capacitance directly from the physical quantities of it. And that's actually a big advantage of the quantity capacitance. And to be honest, it's part of the reason that they developed the constant epsilon naught anyway. It was just a fudge factor to turn the measurements they had into capacitance, and it turned out to have a greater significance than they thought. Now, if we have other shapes, you can see there's lots and lots of fun shapes that you could have. There's really two that we're going to work with specifically. One is a spherical capacitor, and one is a cylindrical capacitor. You can see the spherical capacitor on the top right-hand corner. You can see it's got the spherical conductor on the inside that's solid of radius A, and it has an outer conductor of radius B. The radius A has a certain charge on it, and the radius B has a certain charge on it. You can see that in this case, these do not have the same charge density per plate. So the rules that we had before using, say, sigma over 2 epsilon naught for finding electric field don't work anymore. Boo. You can also see that, I also want to point out in the picture, the one with the blue background on the left, they ground the sphere because basically they're going to have a collection of charge. Ooh, I don't like that picture. The picture makes the inside dark, makes it seem like it's a conductor, but it's not. In that picture with the blue background, that space is just empty space. And the outside, and the only conducting parts are those two magenta circles. Those are the conducting shells. Notice it has positive Q all the way around and negative Q all the way around. And the electric field will go from one edge to the other. Now, it turns out that it'll still be constant. Isn't that weird? I mean, we know that because we calculated electric field that way before. You can see on the bottom in the picture with the light blue cylinder, that is a cylindrical capacitor. In that one, the middle is going to be positively charged again, and the outer edge is going to be negatively charged. The inner will have a charge of positive Q on its surface because that's where conducting charge sits. We don't have an insulator on the inside. On the outside, we have negative Q also. So we can collect charge that way. And you can see in the picture, like right underneath the text, you can see that the positive's collecting in the middle charge on the outer surface of the conductor and collecting on the outer conductor. Okay. The way to calculate those is to use a technique that we've already used before, the technique of calculating potential using the negative integral of E dot ds, and again, you're finding potential difference. So you're calculating from the outer shell to the inner shell. So usually you're not even capturing that outer shell. Just like when we did potential, I think it was a couple of days ago, of two parallel plates, or two cylinders, we pretty much didn't have the charge of the outer plate in our enclosed charge in Quank, so we didn't have to worry about that. But for these, and I think there's one of each kind on the homework, one spherical, one cylindrical, you have to actually calculate V in terms of Q, which you're not given, and usually the Q ends up dividing out somehow. Hope this helps do your homework. If you have any questions, feel free to email me or let me know. Thanks, guys.